I assume you were working together. But a lot of other people appear to have the right setup, but made a mistake in the calculations. In some sense, the teacher, that's a good thing. It shows there's a lot of like independent work going on. You weren't just throwing everything into a spreadsheet or something. Which, by the way, would have been smart. But anyway, but that's fine. I appreciate that people were doing their own work on that. And for some, if you're one of those people, because I've totally been there before, where like you have a suspicion that like you're working with a group of people, and you have a suspicion that other group of people has it right and you don't, but you stuck to yourself and your own anyway. Good for you. That's important. That's an important skill, even if you did get it wrong, and you're usuly right, by the way. We suspect that. But like that's fine. It's important to also develop some. Like independent stuff. So what I did was I marked on here score out of 7 as we're used to. I can probably grade yours like right now. I marked on here a score out of 7 as I usually do, and then I used a complicated formula that is really not worth getting into to determine how many points you got back. Sorry, my computer just unexpectedly shut down, so I don't yet have the thing up that will tell me the average. And then I wrote your new exam grade on there, right? Your updated exam grade. It's not, don't hope for too much. I didn't give back that many points. Like, even if you got it all right, I tried a few things that I thought was okay. So, here we go. Now, so
No.
On average, people got 6 points back.
Oh.
On average, which is not so bad, right?
Hey,
that's pretty good. You a lot less than 73, which is
freaking hope not since you
okay, so here, let's see.
Oh, so this is a game of
Sabian.
Yes.
Briella.
Which Briella? Sable, what'd you say? What? Okay.
Kristen. Benji.
Benji.
Why did you have it? Micah. Eric.
No!
My grade is still a disappointment.
Still did better.
How was I wrong?
More importantly, how is mine more fun than yours? You drew the pictures.
Well, I drew everything.
Probably why. You probably have like a setup.
My life is regret. Why did I come here?
0? Because the origin is the same.
If I stayed at my old school, I'd have all A's and I'd be sleeping every night instead of every other night.
I know. What is wrong with
We're
that?
so stupid.
What?
I said we're stupid because if we were at our old schools, we'd all have all A's and we'd be sleeping every night.
And we wouldn't have to worry about college.
We wouldn't have to worry about college. Okay, well you're smart. You actually belong here, okay, Benji? We get it. We get it, okay?
You guys really don't need my help with physics. You guys need help with planning time and scheduling.
How do you suggest I plan 6 essays, 2 problem sets, 2 web works?
You can't. You work non-stop, you reach a point where the fact you're working non-stop actually limits your grade.
But if I don't work non-stop, I'm gonna like die. My academic
but
career
if
is
you
like
die,
Take a,
then you get
take a schedule.
indefinitely.
That's why you take a handful of CDs and throw a shit ton, get sent home, and then
Is it bad to wish your roommate to die so you get straight A's?
no.
Alright, here. I'll kill your roommate if you kill mine. Who's your roommate?
Excel.
I'm trying to debate if I should ask the teacher for a presentation to go tomorrow. Not this class, my friend's a science teacher. For a presentation to go tomorrow on account of how I was up all of it.
There are two ways to do it correctly, the easy way and the hard way. Of the ones I saw, it looked like most people opted for the hard way. Okay. I did see someone, I don't know, if you got the answer right, I didn't look at it very carefully under the assumption that it's very unlikely you get the right answer for the wrong reason. So there might have been more, but most people I saw were doing it the hard way, which is fine. I saw one incorrect paper that did it the easier way. It's not that easy, but I think it's a little bit easier. The main thing is signs, and if you made a mistake, like if you had the right setup, but you didn't, if I could tell you had the right setup, but something didn't go right, I gave you a 5. But something didn't go right in the calculation, I was hardly about to track that down on 45 kids' papers. So, but it was all certainly a sign error. So the harder way, but maybe more straightforward, is to say, well, let's just say when shift 1 fires, this is the Earth reference frame, you say when shift 1 fires, that's 0, 0, 0, 0. When shift 2 fires in the Earth frame is TX 0, 0. Then you say, all right, now in shift 1's reference frame, you have to transform. Now this is, nice thing is that this always stays the same. And this would transform to, I'll just do it like this, 0, 0. Where of course T prime and X prime, T prime 1 and X prime 1 are just running it through the standard Lorentz transformations. However, this is the trickiest part, okay? The tricky part is these two now have different time coordinates, right? Meaning these events are not happening at the same time in this reference frame. So you can't say this fires when this is at this point, because that's not true, right? This is the point in the time where the other ship fires, but you know that this ship fires exactly when this ship is 2 light seconds away in its frame. So to get it to see when that happens, you need to transform this so that you have 0 as your time coordinate. Then the two time coordinates will be the same. At that point, you know it has to be exactly 2 light seconds away. So to do that, you have to take this and subtract the relative velocity times time of that ship, where the velocity would be velocity of ship 2 in ship 1's reference frame. Which you can get, and this step is the trickiest step, so that you realize you have to get these time coordinates to be the same before you can consider that's when the thing fires. And so to do that, you subtract the velocity times time, which is like an offset of how far to offset where the ship would be at that time, because it counts velocity. Then once you've done that, and by the way, here's the tricky part. This thing is negative. That velocity 1, 2 is negative because the ship is moving this way, right? So, in the way I brought it. So that's one thing that can screw you up. Then once you know that, then you can say that x prime 1 minus b 1, 2 t prime is equal to 2 light seconds. And by the way, in this problem, all the units are nice, so you can just kind of leave them all off. I recommend doing so. Now you have to substitute in for all these things. You have to calculate this one, just using velocity addition, making sure you use the negative, making sure it's negative in the end. You change that to a plus sign, right? And then you have to get those to the Lorentz transformations, and you have an equation in your original variables x and t. Then what you do is you also take a look at a 2's reference frame, where shift A's doesn't change. Shift B's would be this. Okay, now you have to do the same kind of trick to figure out when shift 2 is going to fire. Shift 2 is going to fire in its reference frame when this distance between them is 2 light seconds. But now it's in shift 2's reference frame, so shift 2 is not moving. Shift 1 is the one that's moving, right? So what you have to do is adjust this so that, sorry, it should be 2's, yes. So what you have to do is adjust this so that its time coordinate is now up to t prime 2. That's to say the same as this time coordinate. And you do that by taking 0 and adding to it velocity times the time that you're adding. Once you have that, you know that the distance between these two has to be 2, so you can take x2. And here, this guy is positive. It's the same number as this, except the opposite sign. Because now we're in the other ship's frame, this ship's moving in the positive direction. And so you take x prime 2 equal 2. Once again, you can work through all of that, and now you have 2 equations and 2 variables, because they're both equations of x and t. You do not want to just set them equal. That's not going to be enough information. Well, you can start with that, I guess, if you want to, but it's easier just to solve one and then do the other. Or, honestly, to throw it into Wolfram Alpha. I'm kind of surprised more people didn't do that, although good for you for working through it. When I was double checking, I didn't think of it this way first, so when I was cross-checking it this way, I just put it in Wolfram Alpha. But yeah, it's an equation of two equations, 2 variables. It's not that messy. A computer calculator will make it a little easier. And you can solve for x and t. The one you care about is t. Since this is 0, this t would be the time distance between them. And the sign of t will tell you which one fires first, which, by the way, is different for different people, depending on your numbers, right? Okay, now, the faster way to do it, that doesn't require a system of equations, is to start, so the other way to do it is to start in one's reference frame, where you're at 0, 0, 0, 0, and the shift that is at 0, 2, 0, 0, in one's reference frame, right? Then you transform it, that's my symbol for transform, into 2's reference frame. Using the relative velocity of 2, same as this number, right? The velocity of 2 goes into 1. You transform it into 2's reference frame, you'll have 0, 0, 0, 0. No, you will have to transform, of course. And I'm not going to actually do the calculation, you all did the numbers. So some t prime, x prime, 0, 0, right? But you can actually calculate these exactly though, right?
Yeah.
And then you have to do that same trick, no matter what, you have to end up doing this sometime. Now you found, this is, you found a coordinate for the location of this shift in 2's reference frame. But in 2's reference frame, this thing doesn't move. So therefore, this stays the same over time, right? Which means all you need to do now is move this up to figure out at what time will this be x prime minus 2? Then it'll be 2 light seconds away at whatever time t2 or something like that. Okay, you can again. There's no algebra here, right? This is direct arithmetic. You just figure out, you offset it by this amount to figure out how much time it would pass, and you can find the time coordinate for when this thing fired. Sorry, but that also be the time coordinate when this thing fires because they're in the same frame, right? And then you take this, and once you know that, you'll have a new time coordinate, and once you have that, then you transform it into the Earth's frame and find the time coordinate there. Yes.
I think this was like one of the things that we tried, and like what I did to like verify it, I guess, was I did the same process, but instead of starting in shift 1's reference frame, I had 0, 0, 0, 0, 0, and shift 2's reference frame.
Okay.
And then
You do it the other way.
it works both ways.
Of course, yeah. If you didn't work both ways, then you did something wrong. Probably with the sign, because all the signs have to flip when you go the other way, right? So it was probably a sign error if it didn't work both ways. Of course it works both ways, right?
That's why we didn't go with it.
Oh, okay, well. Yeah, no, it has to work both ways, right? Okay, so anyway, that was that. There's a lot of places to mess up here, right? Actually, it's easier to write it out like this and then break things down bit by bit from here. Let's say write it out like these and then solve for these guys independently. And also easier if they have a calculator helping you out, Wolfram Alpha, etc. But anyway, if you grind through this way, this is how you approach it. Well, kind of a rough problem, but you guys did a good job with it. So yeah, good job. So you get some points back, and and if you still want more points, then hey, we got another project. All right, let me get these back, okay?
I remember that.
Can we meet sometime and see why my method didn't work?
What'd you say?
I agree. I'm very confused on why this didn't work.
Why this didn't work?
Yes.
Yeah, well, my method didn't work. Our method.
I liked the. Oh, I forgot. I was going to look into that more. I liked the idea of using an inner product.
We translated everything into the Earth reference frame.
Yes, but you didn't know. No, that's the thing. There's too many unknown coordinates. You only know that one fires when 2 is away, and it's 2 like 6 away in one's reference frame, and that 2 fires when 1 is 2 seconds away in 2's reference frame. So you don't have a set of coordinates that's good in both reference frames. That you don't know enough in both reference frames to just transform it to Earth. If you just called it 2 in both of them, you're actually secretly shifting origins, and you can't do that. The origin that's the tricky part. You have to choose an origin. Once you choose the origin, then one of the ships is easy and the other one's really hard. And so that's what.
I bet you if we had done what we did in one ship's reference frame versus just
I suspect you kind of repeated the same argument like it's symmetrical, but once you choose an origin, it's not symmetrical anymore.
Yeah.
The other one becomes much harder than the first one. I think that's what happened.
We changed the origin and put time is minus 2.
Now is everyone? Okay. All right. Next. You guys all turn your projects? I didn't get any more fetch emails. So that's good news. All right, good. We're on to the next one. I just got your test. So of course I haven't graded yet. I just got back. I should have it for you tomorrow. Possibly.
Okay, so we took the origin 000.
So
when the ship fires.
This month, okay, fine. This coming month, it's not November yet, is project month. Okay? The reason for that is a very good one. What happens at the end of November? The Fermilab trip. So we better have our project done before that, right? So it's okay. We're actually pretty close to done. This is the last big project we'll have. Then we'll have some smaller things, and we'll start voting, and we'll putting final things together and stuff like that. Okay? But this is the last one of new material in that sense. Okay? So we're almost there. All right. So we already did the tracking detector. I already told you what goes on the outside of the tracking detector. You guys remember? Calorimeter. It's pronounced calorimeter, not calorimeter. Although, I mean, really, why not? I mean, so anyway. So let's talk about the calorimeter. What is a calorimeter measure? Energy. Good. It is not constructed of a soda can full of water. Turns out that doesn't work well with high energy particles. So the basic idea is high energy particles are very, very high energy. I think we mentioned briefly, how do you measure the energy of one then? How do you measure the energy of something? You smash it into something and see how much energy it puts into that thing, right? Now, if we're talking a particle, if you were trying to do that with a truck, I think I used truck as an analogy last time, right? Did I? Was that the other class? You say, look, you take a truck, you smash it into a brick wall, you see how much damage it did to the brick wall, and that calculates the energy of the truck. Right? So, if you want to do that, you would smash it into something. What kind of thing would you smash the truck into?
The ground.
The ground would work. Something that is very massive. Well, big enough, massive, dense, right? I think dense is eventually the word we're looking for, though it does, of course, need to be enough of it as well, right? So you want a large amount of dense material, right? If you try to do it by crashing the truck into like shaving cream, well, would it work?
You would need a lot of shaving cream.
You would just need a lot of shaving cream, that's right. How much shaving cream would you need? I'll let you think about the quantity of shaving cream needed to stop a speeding truck.
A lot.
So we actually have well, you see, shaving cream would have advantages. It would make a nice path right through. You can measure tread length and rotations and stuff like that. Like, it wouldn't be such a bad idea, except for the fact that you would need kind of a lot of it, right? So we actually have a similar issue with calorimetry. So what am I going to want to smash a high energy particle into then? What kind of, give me a substance.
Another high.
Not shaving cream. Give me a substance.
Iron?
Iron. That's nice dense substance. Good. Iron is a great candidate. So also, what's the other advantage of iron besides being dense and heavy? It's also, it is magnetic, but that's not helpful, right?
It's not that old.
It's what? Cheap. Good job. Iron is cheap, right? As dense materials go, iron is one of the cheapest. And it's quite dense. If you guys ever actually lifted iron, they make almost nothing out of iron anymore. Almost everything's made out of aluminum now. You can use metal for good reason. But like, you have like a stage weight or any other kind of weight. Actually, I guess lifting weights as well, right? Like so small, and they weigh so much. Like impossible to lift. It's crazy how dense iron is. So you smash it into iron. Okay, here's the thing. You smash a proton into iron. Great, now what? So obviously we need something else besides just a piece of iron, right?
A way to measure the damage to the iron.
That's right. Unfortunately, we cannot measure the damage to the iron.
Why not?
I know, right? It's the damage, you know, it may be a high energy particle, but it's still just a proton, you know? Like, it's not going to leave, like, you can't, like, measure a scorch mark or something. It's not that, you know, it's not that kind of energy. Yes, Benji?
Is there a maximum of energy one particle can have before, like, disintegrating?
It's an interesting question. It kind of depends on what kind of diagrams are allowed. But something like an electron can carry an arbitrary amount of particles as long as there's nothing of energy, as long as there's nothing nearby for it to interact with. And we have detected cosmic rays with energies up to 10 to the 10 to the 12th GeV. A trillion GeV we've detected in cosmic rays. So they can happen. We're not sure where they come from or how they could possibly happen. We're still really quite confused about that. We're working on it.
Confused?
There was a lot of this project 1 year instead of a poster of it. All for high energy cosmic rays. So high energy just didn't cut it. Okay, so here's how we do it. We have this material that is called scintillator. There's actually quite a lot of different types of scintillating material. The one we use a few different types. It doesn't. It does matter. They have their advantages and disadvantages. But we have a lot of stuff called scintillator. Scintillator is a specific type of material. So I wouldn't say design isn't quite the word, but it has a special property that when a particle goes through it, it takes the atoms in here and causes them, so we don't know enough quantum mechanics yet to go through the mechanism of it. Let's just say when the particle goes through it, it causes the atoms, it transfers some energy to the atoms in there, and that energy is emitted as light. Okay? So it goes through here, the particle goes through here, coming out here comes light, gamma rays. Or actually not gamma rays, just light, but you know, gammas, but, right? So it produces light when it shoots through. This causes it to actually glow slightly, but like you can't actually see it or anything, but right, but it shoots light. So, and most importantly, the light produced is proportional to the energy.
How proportional?
What?
What's the proportions?
Oh, it doesn't matter. You can measure it, right? You can measure the proportion and then you'll know, right? But the nice thing is that it's proportional to energy. Now you shoot a known energy particle in it, you can measure that proportionality. So this is a very, very nice substance, and we've come up with quite a few of them, actually both liquid, gas, and solid. They have to be clear in order to work because you have to have this light that comes out of it. Now, it releases light, and so what are you supposed to do now? We measure the light, and how much light there is tells us how much, and so when I say the light, it's the amount of light, the amplitude. You measure how much light there is, the amount of light there is going to be proportional to the energy, great, you know the energy. Hang on, sorry, I keep on adding caveats. The energy deposited in the material, right?
This is much
Okay, so we want to catch light. Here's the thing. It's just light. You're not going to stand by watching it. Be like, look, I see something. That was a bright one. Right? So what do we have to do with this light? We have to collect it. So first of all, what are we going to wrap the scintillator in? Aluminum foil. Actually, aluminum foil. You basically just wrap it in aluminum foil. It reflects, right? So it's bouncing inside.
I'm assuming that this is like professional grade aluminum foil or not.
You know, I like to hope so, but it sure looks like the stuff you buy at the store.
Well, we use black to keep out.
Use black on the outside. Right?
Well, we didn't have stacks like you guys did. We had just like single.
Oh, you use a single
plastic,
paddle. That's right. Yeah. Oh, it's nice. You would have done it this way.
Yeah.
So,
But we have wrapped stuff in aluminum, and it is actually. It's a heavy grade. It's like the professional cooking aluminum.
Nice.
Yep. That both
But
companies.
that's only because it doesn't rip as easily when you're wrapping it.
Yeah. we have chairs in it.
That both comforts me a lot, and knowing that even professional scientists use aluminum foil.
Yeah,
That's
so you
a
see,
terrible.
science can be straightforward sometimes. It looks just like aluminum, like regular aluminum foil. I think that's actually what they use. Okay, so you wrap it up in foil, except for one part down here, which typically goes to, here's the thing, you have to have some kind of detector, right? But detectors take up space, and you know you don't want holes in your detector, right? So what do you think you can do instead?
Spectrum.
What can you do with this light instead?
Reflect.
If you put a detector right there, now you have a hole in your detector, not great, right? What? Pipe it away through fiber optic cables, right? You've heard of fiber optics? They carry light. So they're usually used light as like a digital signal or something, but it works with any kind of light. So you actually basically use electrical cables that take it away to some nice place where you can actually put a detector. Here you have a photodetector, which is some kind of photon detector. The simplest type of photodetector is called the photomultiplier tube, which is a tube. You send photons come in one end, and okay, so after this project we'll cover the photoelectric effect in more detail, but it strikes a piece of metal which knocks off electrons, and then what you do is you apply a voltage to it that causes what you do is you do this a bunch of times, you do a bunch of these things to knock off more electrons, and each time it knocks off more and more. This is because the number of photons emitted is still pretty small, right? You gotta remember, at the end of the day, these are still protons, or subatomic particles. They're not emitting that much light. So this is needed to amplify the signal to something we can actually measure. Okay, so you put 2,000 volts on this or something, and you kind of ramp it up through this thing that each time it hits this thing and knocks off more electrons. Then these electrons hit things and knocks off more electrons. And you get a whole bunch of electrons shooting up until at the end, you just suck those electrons out of wire and you read a current. Okay? I didn't think to bring it. Dr. Hawker actually has a photomultiplier tube in his office, I think. I'm going to ask him for it. They're about this big. They're useful for a lot of things. However, they have disadvantages as well. They're relatively primitive, so as a result, they are not radiation hard in general. That is to say, radiation hard is resistance. They use the word hard. So they're not radiation resistant. That's it. They usually damage by radiation. They don't work in magnetic fields, and they're big. They kind of take up a lot of space. So there are variants on this that other people have used in different ways. One, for example, is the multi-anode photomultiplier tube. PMT is short for photomultiplier tube. And those are like this, but they're divided into a little grid of like separate channels. So you can multiply, so you can send in up to 256 signals, and they'll process them all at once. It's a lot more efficient. They also have these fancier new things that I'm not going to describe in any kind of detail because I don't think will need it. But the fancier new things are a lot smaller, are sometimes some of them radiation hard, and work in magnetic fields, and cost a lot more. But those are the ones I know about are avalanche photodiodes. Those work off the principle of photon strikes something and it sets off a cascade of more of them and runs across a reverse bias interaction. I don't know much more than that. And vacuum phototriodes. And honestly, I don't even know what a triode is. All I know is that they use these detectors a lot. It's okay, we don't need to know a ton about them. All you really need to know is their characteristics, like are they resistant to radiation, do they work in magnetic fields, how much they cost, things like that, right? Okay, so there's a variety of things you can choose from. But the point is, you take a scintillator, then you, so the simplest scintillator is a piece of plastic, a specific kind of plastic, clear plastic. You wrap it up in aluminum foil, then you wrap that in black so that you don't get any light leaking in. And then you, it's basically black construction paper basically, and it's a little nicer than that. And then, yeah, then the light comes out, you measure the light, and you're done, right? Except, hang on, what energy is it that it measures? Does it measure the energy of the particle going through? It measures the energy what? Well, yeah, it measures the amount of light. But what's the light proportional to? The energy deposited. Let's say the energy left behind in the material. So this is a 10 TeV muon or something going through here, right? Is it going to deposit all 10 TeV into this piece of plastic?
No.
It is not. It's going to deposit a tiny fraction of that. And so it's going to go through and you're going to get a measurement of some tiny fraction of what the overall thing is. Does it deposit that energy uniformly? No. So you can't use it and just try and assume it's like always the same, like trying to extrapolate. No, it doesn't work that way. The energy deposit's not uniform, so it's not going to work that way. Oh, well, that sucks. So what do we need? Go ahead. Oh, we just have a lot of scintillators then, right? Okay. No.
No.
The scintillator is the equivalent of the shaving cream as far as the hydrogen particles go, right? If you're a 5 TeV pion, then this scintillator is just like, right? And you need behind 0.01% of your energy, and you would need you need like 100 feet of this stuff. And it's not that cheap. Actually, you probably need more than that. So that's not going to be useful. So can someone think, what can we do then? What can we do to, on the one hand, we need scintillators. On the other hand, the scintillators are not going to be able to pick up all the energy. We need something heavy like lead. So what can we do? What an interesting idea. How do we lower the energy? Aha. So what if we take a chunk of iron, that's iron, and then put a piece of scintillator? Well, that'll be a start, because then it'll hit this, like lose some of its energy to the iron, and then we'll pick up a little bit of it here. Micah?
Wouldn't you be limiting the type of energy or the lowest amount of energy you can get then? Because the iron
that's not our issue.
Okay.
The low energy part is not our issue. Yeah.
Did you put a scintillator in front of iron and after?
Oh, you can do that too. In fact, building on that point, really, what should you? Here's the thing: iron will knock off some of its energy. The scintillator will pick up some of that.
So you have a scintillator and iron that's scintillating and making gas.
Right. So you keep on going like this.
Interesting.
Alternating. So you alternate what's called the absorber and the scintillator.
How would you do this in sphere stuff?
And it switches back and forth. And so now as the particle comes through, it blasts a whole bunch of this energy into the iron. You pick up a little bit of the scintillator. A whole bunch more into the iron. You pick up into the scintillator. A whole bunch more into the iron. You pick up into the scintillator. And so on and so forth. For 30, 50, 60 layers of this stuff. Okay? This design is the most common design, and it's referred to as a sampling calorimeter. Why is it called that? Because it only samples the energy. It does not measure all the energy, right? It samples the energy at specific points. What do you do then? A lot of theoretical physics modeling, a lot of testing, right? A lot of computer simulations to get everything lined up.
Do we have to do any
comfortable that when a particle comes in from these points you sampled, you can figure out what the particle's energy was. Okay.
What are all the calculations you have to do?
Not going there.
Don't
I never did chemistry physics anyway, so I don't even know what's done. In fact, I spent a lot of time just trying to find the one equation that you have there. It took me so long to find. Yeah. So no, I don't even know is the answer. But there's a lot that goes into it. A lot of work. But in principle, you can do it, right? With test beam studies, with physics simulations, computers, all this stuff, you can figure it out. However, as you can imagine, it's not perfect, right? Because even no matter how well you do simulations, still you're only measuring some of the energy, right? So there are alternatives to a sampling calorimeter. Can you think of what would we really want to do? How about what if? Start a question with Dr. Dong. Is there a material that can absorb energy better than iron? I mean, not a lot.
Osmium.
But that's not what we really need.
Iridium.
Right. Is there a material that what does it need to be an absorber? Dense. Is there a material that is dense and a scintillator? The answer is yes. There's a few of those. And so the other option to assembly colorimeter is the homogeneous colorimeter. The homogeneous colorimeter looks like that. And is made of, for example, a common, well, a big one right now, the CMS uses it, is lead tungstate. Lead tungstate is a scintillating crystal. It's grown in crystal form. It scintillates. It's also made of lead, and therefore is very, very dense. And so you can actually use this as both. And can someone think of a drawback to the homogeneous colorimeter?
Guessing it's expensive?
It's horrendously expensive. Not only is it horrendously expensive, lead tungstate crystal apparently has to be made in Russia because everywhere else the health restrictions are too strict.
Ew, I don't want to go to Russia.
This stuff is, and it's probably not just Russia, but Russia's a major collaborator, and I think they're the only major collaborator where it's even legal to do all these processes. So we don't love stuff in Russia. Yeah, that's because this is very dangerous stuff to work with. Lead tungstate crystal. So it's expensive, and you Russians on your team. I'm sure there are other places, and maybe it was possible in other countries, but easier to do in Russia because So but anyway, now there are other ones besides lead tungstate. I have not heard of any existing colorimeters that use them, but you can look it up and see what other dense scintillating materials there are. That can be used for this. But yeah, they tend to be very expensive, whereas iron is dirt cheap. And scintillated are pieces of plastic. It's not that expensive.
Does it have...
Martin, thank you, when you were talking about being upset about using the store-bought oil, the plastic that we're using is the same plastic that's used in fiber optics. So it's a light pipe. Yeah, basically, you probably have a ruler made of this type of plastic that is a light pipe.
This Fermilab.
So any place you hit with a light, it will only come out the sides.
Yeah.
So all you have to do is make sure the sides are reflecting back in.
Yeah. Yeah, that's right. That's right. You only have to line the sides.
Yeah.
Yeah, that's right. You can get them at Fermilab. Fermilab has village made out of scintillator. You can tell they're orange or green. And if you get them in a very dark room and shine a light just on that, you can see light coming out the ends. Yes, man.
Lead tungstate is very dense, and the white plastic would not be very dense. Is there a middle ground?
Probably. How do we figure out this middle ground? What a great question. So here's the thing. Actually, I'm not right there yet. Here's the other problem. So, there's a lot of particles we want to measure the energy of. Give me some of them. Go ahead. What are them? Muons. Okay, actually, the muons, unfortunately, we're not going to be able to do.
What?
Because unfortunately, muons punch through everything. Just no matter what. You can't stop them. They just go through everything. Sorry.
Wait, that would have been nice to know.
What? Electrons, go ahead.
This would have been useful information.
Up, down, quartz.
You can't detect quartz, remember? What else?
Tau.
Tau, yeah, those are way too unstable. They have to be the real life ones, or else they'll decay.
Oh yeah, we were originally going to do taus.
You didn't do tau?
No.
What?
Because we did everything under the sun other than taus.
Neutrons.
Neutrino.
Not neutrinos, we can't detect those, no one can. I mean, there's a big neutrino detector to detect 1 in a trillion or something like that. Not helpful for us. Come on, there's a big one, it's all around us.
Air.
Dark matter.
Photons, there we go. And then these you wouldn't get, but pions and kaons are long-lived enough that they'll make it to the detector with them. You remember that Lorentz boost you got with the muons? Same kind of thing happens. The muons too, but we can't get those because they're hopeless. Okay, so here's the thing. Here's what we discovered. Of these guys, electrons and photons, interact easily. That's because their mass is very, very low. And they interact electromagnetically. So we call these electromagnetic particles. Even though the other ones I know are also charged and stuff, these are referred to as electromagnetic particles. Okay? And that's because they interact so easily. And when they interact, they do it like crazy. So if an electron comes through and it's like, look at atoms. They're like, look at another atom. It like shoots off all its energy really fast. Okay, a photon does the same. Because it's not just, oh, right now we're going to find the diagrams, good. So it's not just that when an electron is near another electron, it can interact with the electron like this, and that interaction causes it to radiate a photon in a process called Bremsstrahlung. Don't worry about that. But it is called Bremsstrahlung. Bremsstrahlung is German for braking radiation. They never call it braking radiation, they call it Bremsstrahlung. So like whatever. So right, so this happens really easily. And then this photon here, you know what it can do? It's a high energy photon, it can pair produce. And these pair producing guys could interact and Bremsstrahlung some more and pair produce some more, right? And so basically as soon as an electron hits a piece of something dense, what happens to it? Yeah, it makes a whole bunch of particles, photons and electrons, and a few other stuff too. It doesn't have to be electrons, it can make some hadrons and stuff too. And so it creates all these things, like all these things keep on radiating, splitting off, right, and radiating more stuff, and it becomes a particle shower. That's actually what it's called. It's called a shower. And it's a better name than a lot of their names, you have to admit. Right? There's a particle shower, but like a shower. They all go in the same general direction because of conservation of momentum from that original electron, right? But they shoot out in a shower, like within a certain radius. So when you're measuring this thing, you're not measuring one particle. You're measuring like 10,000 of them, right? Because when the one particle hits, then boom, this whole shower shoots out. It's actually more than 10,000. Forget the shower max is like like that. Forget, yeah. We'll get to the muons. We'll get to detectors at the outside.
Thank you.
Good question. What
Wait,
we'll
does
do
that
is
mean
we'll
we're
turn
going
that
to
to
do
our
separate
advantage
detectors for
because
photon
the
and
calorimeter blocks everything else and
tube?
everything outside is all muons. And that allows us to measure them really nicely. Yeah. Okay. Micah?
Does that mean since we're doing protons and muons sort of thing, like all of them, does that mean we're going to have two detectors of muon?
No. You're going to get everything. This is stuff coming out, right, of your interaction.
Yes.
All sorts of stuff comes out of your interaction. Oh, you're going to have another detector on the outside for the muons.
Okay, that's what I was asking.
That's not this project right now. Okay. Because, so now these guys, they interact really quickly. Now, these guys interact more slowly, and we refer to them as hadronic particles. That one actually is a good name because they're all hadrons. Okay. The reason is they're much more massive. So when they're massive, they go through. They radiate a thing, but they don't just explode like crazy the way electrons do. Right. Instead, they kind of like release a little bit of energy and keep on going. It doesn't change their direction. They don't splinter as easily because they're composite particles and all this stuff. But every now and then, because these are hadrons, how else can they interact? They can interact with strong force. They're made of quarks. They can interact with strong force. So every now and then, one of these guys hits a nucleus, and when it hits a nucleus, it goes nuts. It usually like rips the nucleus apart and shoots stuff everywhere. So these guys are a pain to deal with. They're hard because of that nuclear interaction. When they create those nuclear interactions, they release some energy that can't be measured. It goes into recoil. Let's say it hits the nucleus, makes it bounce, but it doesn't go anywhere else. Then you lose that energy. Some of it goes into neutrinos, because some of these things can produce neutrinos, and then that's lost. You can't measure that. And so it's harder to measure these guys. So these guys are easy. These guys are hard. But we want to measure both of them. Here's the thing. We can't just give up on the hadronic particles. We got to measure them. But we really want to make sure you get the easy guys. Right? So what's our solution? How can we do that? So the easy guys, the problem is if you build a giant thick detector, right? Then the easy guys will be gone by like layer 2. You know? And the hadrons will need, 25 layers to go through. So what can we do? Good. What we actually do is we split it into 2 detectors. Okay? So you remember here's the center, right? You put the tracking detector, you guys already did that, right? Then around that, we put the electromagnetic calorimeter. EM for short. So the electromagnetic calorimeter, they usually call it the ECAL. I'll probably call it that by habit. And that one is small, and it'll interact with everything, but it's designed to get electrons and photons, right? That's its whole point. And then around that, we're going to put another detector, another calorimeter. That's the hadronic calorimeter, or HCAL. This one's going to be a lot bigger and thicker, and is going to pick up everything else. What's the advantage of this? What's the advantage of splitting it into two?
You don't need to pay as much money getting right tungstate for the bottom one.
Right, exactly. You can make the EM calorimeter, because it's a lot smaller, you can make it a lot nicer, and then make this thing kind of cheap, because it's just not worth it. You know? So you can put so for example, the CMS detector, they put the EM calorimeter is actually entirely lead tungstate. Very expensive. And the hadronic calorimeter is, I think, brass and scintillator. And so it's like, oh yeah, and then on top of it. Actually, many tons of it, of course. Yeah.
Why would you use other materials?
What a great question. Let me tell you. Because how do we know what material to use, period, right? It's not just density, of course, right? There's a quantity that goes along with it. And the names of quantities is very important. There's radiation length and interaction length. Okay? These are distances, okay? So, here's how it goes. In one radiation length of material, an electron loses, loses 1 minus 1 over E of its energy as a fraction. Let's say its energy drops from what it was to 1 over E times what it was. So if it started out at 1, it would drop down to 1 over E in one radiation length. That's a distance. So a radiation length is a way to kind of normalize these things. Now, different materials have different radiation lengths. So you want something with a radiation length that is short. Good, whoever said that. You want something with a short radiation length. That means you disperse the energy really fast. Why are we so concerned about getting the energy out fast?
So you don't need tons of
Right, but in addition to, you want to save on your detector. What's the big problem with your detector?
The larger it is, the more expensive it is.
Right, the larger it is, the more expensive it gets, because you have to increase the surface area as you increase the radius, right? So getting it compact saves you money, right? And it can be worth it to spend on more expensive material on the inside if it means you don't have to build as much out of it. Yeah.
So for the EM calorimeter, how does it?
Oh, it does the same thing. That all these things, when they go through the scintillator, they'll scintillate you to detect the light from it. It's just really nice and easy to read the electromagnetic particles, and they're dispersed really fast. So the electrons, a photon, for example, hits the EM calorimeter and it's gone, right? The electron hits it and it's gone by the end of the EM calorimeter. A pion, say, goes through and it goes through and works its way through the hadronic calorimeter before it's finally absorbed.
So then, like, even all of these things produced here will get absorbed by the EM calorimeter.
Right. It will get. The pion will go through the EM calorimeter. It will leave some energy, just not that much. And then the big old honkin' hadronic calorimeter will have to pick up all its energy. It's just hard to absorb hadronic particles. They take a lot longer. Yeah.
You only have to build as to absorb as
Right. Now, the rule of thumb is more radiation. Okay, so by the way, gotta guess what interaction length means? It's the same thing except for hadronic particles. So this is for the EM particles. This is for the hadronic particles. Right, remember, the hadronic needs to be a lot thicker. This is 1 Why? The interaction lengths for a given material are much longer than radiation lengths. So all you need is a table. Ah, good, I gave you one. It's in the document. It's actually a very, very extensive table with a huge amount of articles. And it gives you, among other things, their radiation length, their interaction length, their density, their Moliere radius, critical energy, all sorts of stuff. Yeah?
Why do you have to absorb all the energy?
Because if you don't absorb all the energy of the particle, A, your muon detector will work very badly. We'll see that later. And B, you won't get a good energy measurement, right? Because your calculations on these things are under the assumption that you caught all the energy by the end. If you didn't, you really don't know what kind of particle went through here, right? Basically, if you can get all the energy, then you can kind of refit this curve based on simulations and stuff. But if you don't get all of it, you don't really know where you are on the curve. It's much, much harder. So you basically have to stop the whole thing. Yeah?
When a photon passes through a scintillator, does the scintillator emit the exact same light?
It's the same frequency of light. At least the frequency is the number of photons that makes the difference. So it's very, very useful for dealing with it, because then it's directly proportional to the brightness of the light. Okay, so here's your basic challenge then, right? So your calorimeter is going to be designed in layers. If you have a sampling calorimeter, it'll be a lot of layers, right? Homogeneous one will be more straightforward. In addition, you have to break it into segments. In like, wow, I already drew all of that. Okay, so in addition, so if this is the interaction point here, right? Your calorimeter is going to be in layers like this, probably, if it's a sampling calorimeter, right? But in addition, you have to cut it up this way, because you need to know, you can't just measure all the particles at once, right? You need to split it up so you know this particle went here, that's its energy. This particle went over here, that's that particle's energy, right? And so as a result, you end up with clusters of energy that you can then associate with particles from the tracking detector. So you need to split it up this way, and then, I don't have a third dimension, but like also this way you have to split it up. So you have to give segmentation, is the word for that. And typically it's in phi and eta. You remember what eta is? The pseudo-rapidity. Yeah. And we'll have to talk about it more another day. But it's just a calculation that you can make from the angle theta. So phi, remember that if this is the beam pipe, phi is the one that goes around the barrel of the cylinder, and theta is the one that goes up from here or whatever. Theta or eta go this way. Okay, so you're gonna have to split it up now. That's what you have to build. A few other things. If you want, you could put this thing inside the solenoid. CMS does that. Right? In other words, remember the solenoid in your tracking detector? You can actually put it around the whole calorimeter instead. Why would you do that? Save space, allows you to make the calorimeter smaller. Also, solenoids are thick, and so that's less material that it goes through before it reaches the calorimeter. What's the downside? You have to make it magnetic field strength safe, which is going to increase your price. And, well, come on, you know how solenoids work. You have to make a gigantic solenoid, so that's very expensive, right? You may choose to do that if you want. So you have to work under the, you know what your tracking detector looks like, right? So save that space is off limits, unless you decide to move your solenoid to the outside, which you can do, then you can move into that space where your solenoid was, right? But other than that, you leave your that tracking volume empty, and just start building around it in probably spherical shells or cylinders and discs, right? And you're going to build your way out from there. So the main thing you want to decide is to figure out what materials you want. I gave you a list of some costs and some materials to work with, but you're always welcome to find more. Just see me for a price estimate. Okay? And anything else like that. I'm looking at a Tuesday day for this. But we'll see. Tuesday, Thursday, right?
I just ruined your life.
I don't have a life.
That'll give you an idea in between.
Yeah, I'd like to.